Hey, we have got another example here talking about conservation of mass. For this one, we have steam at a pressure of 80 bar and a temperature of 440 degrees Celsius. It's going to enter a turbine that is operating at steady state with a volumetric flow rate of 236 cubic meters per minute. You can see that shown right here. So this is steam coming in. 20% of that entering mass flow exits through a diameter of 0.25 meters at a pressure of 60 bar and 400 degrees Celsius. The rest exits through a diameter of 1.5 meters with a pressure of 0.7 bar and a quality of 0.9 or 90%. We are going to find velocity at each exit duct in meters per second. So we got a lot of stuff to keep track of here. Before we get started, this problem's got some keywords in it, so let's pay attention and see what we find in our problem statement. First, it tells us we are operating at steady state. Definitely want to pay attention to that. And do you remember what that means? That means nothing changes with time. We also are given the volumetric flow rate. And we want to pay attention to this 20%. Then we've got all these digits, these numbers. Obviously, we need to pay attention to that. And then we've got a quality of 90%. Okay, so steady state is going to be the main keyword in this problem. All right, and then you can see what happens here. So that steam's going to come in. Here is where 20% of the steam that's coming in leaves, and then the rest is going to leave over here. And we've got 90% for quality. That's this X3 number. All right, well, let's get started. So first, let's write down what we're looking for. We want velocity at each exit. So if this is 2, this is 3, we want V2 and V3. That's what we're looking for. Next, let's write down some of our equations. We've got all these mass flows that we're talking about. We know M2 dot is 0.2 of M1 dot. We don't know what M1 dot is, so let's write down an equation for that. Remember, the M dot equation is rho AV, where V is velocity, and that is also equal to AV over little v, or specific volume. So we'll probably need to use this equation, one of these versions. We know we have steady state, and from our notes when we derived our equations, we know if we have a steady state problem, that if we're dealing with conservation of mass, that means that we can say that the sum of the inlet mass flows has to equal the sum of the outlet mass flows, like that. Okay, so those are going to be a couple of our equations. We're going to need those. Now first, in order to figure out the velocity here, I need to know how much flow is coming out of this exit. And I know M2 dot is 0.2 times M1 dot, so it's 20% of your inlet mass flow. So if I can find M1 dot, then I can find this mass flow rate that's coming out here at exit 2. Let's do that first. So we need M1 dot. Now if we look, let's look at this equation here. We're already given AV, right? The volumetric flow rate that was given, that's 236. So we have this numerator part. We don't have specific volume, but we do have the pressure and the temperature. So what's that going to let us do? That's right, we're going to head back to those tables, everybody's favorite. So let's write some of that down. So we need V. So we're going to use P1 and T1 and go to the tables. Whoops, forgot the 2 part. For our tables, we got our pressure and our temperature, so let's come over here. This is the saturated water table, just to show you how we get to superheated vapor. So our pressure was 80, This is our saturation temperature. Okay, so 295.1. Now we need to compare that with our temperature, which our temperature is higher than that. We are at 440. So remember, if we were to draw that, that's a terrible vapor dome, but anyways. We've got our temperature up here at 440. So this was the saturation temperature. I've already forgotten the number. 295. So this was 295.1. Now in order for these to intersect, we're going to be over here, superheated vapor. That's going to send us to the superheated vapor table, and in that table we go, here's 80 bar, our temperature is 440, we need V. So that's this number right here, 0.03742. Okay, so that's kind of the thought process there as we go through and find the value for V. So this is table A4 if you have the Moran book. And V, we said, was 0.03742 cubic meter per kilogram. Now we've got that. Let's go ahead and use that in the mass flow rate equation. So M1 dot is going to be 236 cubic meters per minute. We're going to put that over V. So 0.03742 cubic meters per kilogram. Now let's stop and think about this for a minute. Do we probably want to leave minutes in here? Probably not, right? We don't ever use minutes. Everything is always in seconds. So let's go ahead and convert this over to seconds. Now we have that. So this will get rid of minutes. Now if you look at your units, the cubic meters, that goes away. You're going to be left with kilograms per second, which is what we want for a mass flow rate. Doing the numbers, you get 105.113 kilograms per second. So this is your mass flow rate for the entrance here at 1. Now that we've got this, now that we know what's coming in here, we can figure out what's coming out at 2, right? Because we know M2 dot is 20% of M1 dot. Let's do that step next. So we have 0.2 times M1 dot. So just multiply this number by 0.2. And then if we do that, we get 21.022 kilograms per second. Alright, so now we can look at exit 2. So let's focus on exit 2. And we'll get our velocity. So we know that at exit 2, M2 dot's got to be A2 V2 over specific volume at exit 2. Our pressure here, notice our pressure is now 60 bar, temperature has gone down to 400. So now we've got these conditions. Now we're looking for this. This is what we're looking for, this V2 right here. So if we can find M2 dot, which we already found that, so that's good. If we can find the area and specific volume at the exit, we'll be good to go and we can find velocity. Area can be found because diameter was given to us, so area will be really easy to find. We just need to again find V2. Now again, in order to find V2, you're going to have to go back to those tables. We need to figure out what we've got. So again, you would start off on that saturated water table. Our pressure is 60. And that's the temperature table. Let me get the right table, guys. There it is. Okay, sorry about that. So we're at 60, right here, down at the bottom, and we've got 275.6. This is our saturation temperature. Now we need to compare our number to that 275.6. And we are at 400, so again, that means we've got superheated vapor. Okay, so 275.6 was that. So 400 is greater than this. Therefore, we're at superheated vapor. And that takes us to table A4. Again. And then you just look up your values here. So we're at 60 and a temperature of 400. Here we are. Here is pressure of 60. We've got 400 right here. So come over here. We get 0.04739. And I'll put it over here. And that's kilograms per, not kilogram, that's not the right units. Cubic meters per kilogram. There we go. So that's what you get for V2. So we're going to take this number, we can plug it in here along with our area, and then we'll have M2 dot. Actually, we already have this value. Let's put the value in first. So we got 21.022 kilograms per second. For area, we have the diameter. Diameter is 0.25, so the area equation for a circle is going to be pi r squared. So we'll have pi times 0.25 meters divided by 2, square that. Multiply that by the velocity at that exit, divide it by the specific volume that we just found in the table. So 0.04739 cubic meters per kilogram. Now we have one equation, one unknown. We can solve for V2, which is our velocity, which we were wanting. That's going to give you 20.3 meters per second. All right, so there you have it. There's our velocity for exit 2. Now we need to do the same thing for exit 3. We do not know the mass flow rate at exit 3. All we were told was the mass flow at exit 2 was 20% of M1. So let's go ahead. We'll just use our conservation of mass equation. Because remember, we were steady state. I know I keep moving this, sorry. So that means we have this equation here. Sum of the mass flows in has to equal sum of the mass flows out. That means we can write M1 dot equals M2 dot plus M3 dot. So now I'll just solve for M3 dot. So we're going to have M1 dot minus M2 dot. Plug in your numbers, you get 105.113 minus 21.022. Both of those are in kilograms per second. That gives you 84.09 kilograms per second. That's your mass flow rate at exit 3 from that turbine. Now let's analyze some things and get our velocity. Okay. For exit 3, let's look at what we were given. We were given quality. We were told quality is 0.9. Our pressure has gone way down to 0.7 bar, and the diameter is up, larger than the second one. It is 1.5 meters. So let's write these numbers down. All right, so that's what we have. Now, looking at this quality right here, this should tell you what kind of substance we've got here. Do we have a compressed liquid? Nope. Do we have superheated vapor? Nope. We've got a quality given. So if a quality is given, that means we have a liquid vapor mixture. Because you're only going to get a quality if you've got a liquid vapor mixture. This means when we are finding our specific volume, then we need to go to table A2. So that's going to be the saturated water table. So that's that main table we always keep starting with. And remember, that table only gives you the values for specific volume. at the point where the quality is 0 or 1, so the F and G points. That means we have to use this equation here to find our specific volume at this set of conditions. All right, so you're going to use the table to find VF and VG. That's going to come from table A2. And let me find that table. I've got tables everywhere. So we are at a pressure of 0.7 bar, and that's what we know. Actually, we want to use table A3. A2 is the temperature table. We don't have the temperature, so let's go to A3. A3 is the one with the pressure in the first column. So with 0.9, here we are. So we're going to come over here. This is VF times 10 to the 3. Okay, so we're going to have this number for VF. We need to divide that by 1,000, and then VG is 1.869. So those will be our two values that we are going to use. And let's go ahead and write those down. So 1.036 cubic meters per kilogram. Remember to divide by 1,000. Plus X, which is 0.9, times VG, which was 2.365, minus VF, so it's 1.036 divided by 1,000. That's, both of these are cubic meter per kilogram. Quality, remember, has no units. So with this is going to be our V3. So you get 2.129 cubic meters per kilogram. Now that we have our specific volume, we are going to go back to our mass flow equation and use that to solve. Let me get another piece of paper here. So with this one, remember, we're going to have M3 dot is going to equal to A3 V3 over little v3. M3 dot, we already found that. That was 84.09. We did that right here. So we have that. That's going to equal A3. The diameter at this exit is 1.5. So we're going to have pi times 1.5 divided by 2. That gives us the radius. Square that radius. Multiply it by the velocity at the exit 3, and then put that over the specific volume. So 2.129 cubic meters per kilogram. We're almost done. Finally, there's V3. We need to solve for that. So the velocity that you get is 101.31 meters per second. That is your mass, or your velocity for your mass that's flowing out at exit 3. All right. So you can kind of see how those velocities change. The velocity at exit 2 was only 20. This one is 101.3. All right. So hopefully that gives you a good idea of how to use your equations, how to apply steady state, and use the tables again. Everything always goes back to those tables. All right, guys, that is the last example for this section. The next video we will add on to this material. See you next time.